All right, in pre-calculus 30, proving identities, very, very important. I need you to understand, though, that proving identities, again, is not like verifying. I think we talked about that before. You might have seen that in your homework for 6.1 or 2. But verifying is simply plugging a permissible value in and testing to see if the left side equals the right side, to see if the equality holds true. So if you pick a value and you plug it into the left side and you get this value, okay, that it simplifies to, and then you do the same thing to the other side, and the values are the same, then that statement could be true for all values of x. So that's verifying. What we're focusing on now is proving. So that means we don't want to treat the expression as an equality. Okay, we're trying to test whether it's equal or not. So, for example, if I said 5 times 2 equals 10, okay, and we are assuming this is equal, we know it's equal, and if I did something like this, divide by 2, this would be 5 equals 5. Because this is equal, I can do these operations, but this is not what we're doing in proving. We cannot mix the two sides of the equal sign at all. Boys listening? Okay, no talking. I need you to glued in. I need you glued in. You're not going to have a chance at this if you don't listen, okay? I'm just promising you, okay? Not a threat. I'm just saying you're not going to have a chance if you don't listen. So we are not using the equality principle. We're not using equality to prove an equality. We can't do that. So we cannot mix the two sides of the equation. And as a matter of fact, I don't like to call it an equation. I like to say, because they do often have this equals this, prove it. So you're not using that equal sign, okay? You have to just focus on each side separately. So we're proving identities. We cannot assume it's equal by using these sort of operations. So we can't do this. Can't mix the sides. So here's an example. We've done sort of something like this already. We've led up to this. But here's something that, in words, we're going to try and do. So if the left side of the proposed equality is this, 1 minus x squared, okay, and the right side of the proposed equality is sine x cos x times cotan x, then we are trying to really adjust or manipulate or rearrange one side at a time to try and make them look the same, to make them look equal. Because right now, these are not equal statements, okay? They don't look the same, right? They're subtraction instead of multiplication. We've got a cotan, we've got a, all this sort of stuff. So we have to change one side or the other or both to make them look equal. So here's what I'm saying. What we could do for this one is we want to explore our identities to try and substitute or rearrange the statement to make it look like something else. So 1 minus sine squared x. What jumps out at you from your identities list? Cos squared. Okay, so I am going to simply rewrite this as cos squared x. So assuming for all possible values of x, this statement right here can be written as cos squared x. We know that's an identity. You good? Okay, you good with that? Now, I could rearrange this a bit more. I could split this up. But let's go over to the right side and see what pops out over here. Let's do the same thing. And I got sine times cos times cotan. So what jumps out at you here that you can kind of like substitute or rearrange?
You can cancel out the sine because cotangent will have sine on it.
Okay, so I'm going to focus on that cotangent, right. Our reciprocal identities, part of that is the fact that, I'm going to write this, just do one step at a time, okay. Cotan is cos x over sine x, right?
Yeah.
Okay, so these are all multiplied. And when you start substituting identities in, then things pop out at you, right? Literally, they just pop out. And so, yeah, you kind of mentioned this already, that sine x on top and sine x on the bottom, those divide out to give you 1. So it's like they divide out and they're gone. So this is cos times cos, which is cos squared x. So I have rearranged, I haven't switched anything over from side to side, but I have just simply worked on one side, worked on the other, and I can show that these are the same. And guess what? If you didn't touch this side over here, let's just back up the tape here, and let's say I didn't do anything to this side, I just focused on the more complicated side, which is actually a really good tip. You could do one more step over here and say, hey, do you know what? cosquared x actually equals 1 minus sine squared x. So you could do that step on the same side, and look at, they're now both showing to be the same. So this is the idea here. This is what we're trying to do, okay? And I did that down here as well, okay?
QED.
Now, I want to talk to you about QED. Do you know what this means or stands for, or why I've written this here?
It has been proven or something.
Yes, yes. So this is Latin quod erit demonstrandum, which means, yeah, quod erit demonstrandum, and I think I'm saying that correctly, but it means what was to have been demonstrated, okay? So I have demonstrated what was proposed to be demonstrated. So you don't have to, you're not going to lose marks, but when you're done a proof, at the end of your proof, you should put QED to signal that you're done. It's kind of like circling your answer, showing you're done. The other thing that I appreciate or would encourage you is if you just highlight your finished sort of product with the other finished product, even if it's the original, to show that they're the same now. I like you to highlight that if you can. But anyways, QED is not necessary, but it makes you look smart. All right, and it signals that you're done your proof. It's like, I rest my case, right? You're proving in a court of law here, I rest my case. I'm finished demonstrating what was to have been demonstrated. Yeah.
So would you prefer the answer to be like how you have it up there, or would you just prefer us to like do both sides? I know like cosine.
Yeah. Okay, so should you work on both sides or just one side? I will say that in part of my instruction, in my tips, and I think that's okay, not here, but yeah, because you asked the question, my suggestion would be to pick one side only, the more complicated side, the more complicated looking side, because you got more to work with, and then try and keep manipulating it until it looks like the other side. Now, sometimes you may want to work on both sides, but most of the time you pick one side and just focus on that. Because if you change one side and you're like, I don't know, this doesn't look good, then you change the other side, well, you're going to be maybe further apart. Things are going to get more complicated. It's kind of like if you have a friend and it's dark out and they're like on the other side of the park, and you're saying, I'm trying to find you, like shout or keep talking. It's easier if your friend just stays in one spot and you follow the noise. If you like, oh, I heard the sound over there, and then you walk and your friend is also walking, now the sound's over there. It's like, what, wait, what? And then you turn and they turn, and now you talk again, and your friend's moved over there and you've moved over. So it's harder to find each other. So that's kind of the example I use. So just pick the more complicated side and manipulate that side. Good question. That would be my my advice. All right. Notes on proving. To prove an identity is true for all permissible values. It is necessary to express both sides of the identity in equivalent forms. That's what we just did. So both sides of the identity to be expressed in equivalent forms. 2, again, remember, you cannot perform operations across the identity or equal sign. You can't do that. You can't assume it's equal to prove it's equal.
So that's like doing stuff like canceling like a sign.
Yes, you can't take a sign from both sides and say, oh, they're gone. No, because you're assuming the equality by doing that. So you can't do that. Another question?
When you say like equal sign, is that like also like greater than or less than anything?
No, not greater than less than. It's always just going to be an equal sign. So it might look like this. So prove, like it might say prove this is an identity. So prove that this left side always equals the right side. That's what it's going to say. So you can't use this as an equal sign. You have to prove that this side equals this side. Okay?
Yeah, like will there be
No, there's no greater than less than. Don't worry about that. So there are tips and tricks to prove identities in an efficient manner. We'll discuss those as we move through the lessons. The first one I already gave you. Pick the more complicated side if you have a choice. Okay, so just a tip on verifying. Again, I don't really want to spend much time on this because this is not really for this. But if you're asked to verify, and in section 6.3 you might be, that means you pick a value that is permissible and you test both sides to see if this might be an identity. Okay, so I'm actually just going to show you the work for this question. I'm not going to spend the time on it. I'm just going to show you the kind of the finished product for this. All right, so just to show you, there's like one question where you have to verify that this might, it says verify each potential identity This one says by graphing. That you might have one that says by choosing a value and just seeing if the values are the same. So you'll want to identify, you don't want to pick a value that's non-permissible. And remember, you can't divide by 0. So tan x is sine x over cos x. So cos x cannot be equal to 0. So you'd have to figure out, well, what values for cos x, are equal to 0, and that x value, you can't choose that one to test. You also, cosecant is what? Is 1 over sine. So sine of 0, you can't have that one either. So the non-permissible values would be these 4 that you cannot choose, but you can choose any other one. All right? So you normally don't have to state which values are non-permissible, but you just can't choose ones that are non-permissible. So what would be safe would be like pi over 4 or root 3 over 2 or 1/2. Those would be generally safe because generally they're okay. Nothing is 0 for those ones. So I've chosen pi over 4 here, and I'm literally going to put pi over 4 in for x in both sides and evaluate using the unit circle. And again, fast forward, here we go. I'm just simplifying, and look at that. The left side equals 1/2 when I substitute that value in, and so does the right side. So verifying this way, okay, you should have the same number, that's the determined value on both sides of the equation. That's verifying. Now, if it says verify graphically, then what you do is you get on your calculator, graphing calculator, and you let y equals, and you type this in. And then you let y equals, and you type this in. And both graphs should be the exact same. They should be the exact same graphs. So that's how you verify both algebraically and graphically, okay? Short section. Questions?
No questions.
No, I can't move my head. No, I don't want you, put your phone away. No pictures. No. Okay, so now we're going to prove, so this is what 6.3 is all about. It's not, the verifying is the minor part of it. The proving is what's important. So one of the tips I already mentioned, you should choose just one side and manipulate that and work that one down. This one is pretty obvious that you can pretty easily do the right side, even though this is not the more complicated side. You can change this into sine squared if you want. That's pretty easy. But if they both look really complicated, I would suggest not working on both sides, just one side. So watch this. I'm going to pick the left side because there's just a lot of material to work with, right? It's very complicated. It's like, oh, that's complicated. Well, that's the one you should pick because you can change tan into something. You can change cosecant into something. And when you change these into, let's say, in terms of sine and cos, you might be able to cancel a bunch of things or divide out a bunch of things. So I'm going to focus on the left side, and I'm going to write tan as sine x over cos x. One of my identities. I'm going to leave cos x right here, and you're going to be able to see that we're going to be able to cancel something out, divide something out. 1 over cosecant is 1 over sine, right? Okay, so that's your first step. And showing each of these steps, guys, is super important because I'm not concerned that you have the final answer of the left side equaling the right side because, like I say, for most of these, if not all of these I'm going to give you, it will be able to be simplified that way. These are identities that you can prove. So it's the steps that are most important. Okay? So you have to show your steps. All right. So you would show me that you're going to cancel out or divide out cos x like that. And then you're going to have sine x. And then this is going to be times sine x over 1, right? Because you flip and multiply this fraction. So you can do kind of those two steps at once. Okay, and that kind of comes up there. And so what we have is sine squared x. The last step can be done on either side because you're going to either change 1 minus cos squared x into sine squared x, like one of our identities, or you're going to turn sine squared x into 1 minus cos squared x. So either one. I'll change this side just to save some screen here. So you see how this is an identity? That goes to sine squared x.
Yes.
So now I have this and I have this. And right near the bottom, you would write QED, and that means you're done. And you've showed sufficient steps for that. Does that make sense?
Yeah.
Okay? Okay, so I'll give you all the time in the world to copy this one down. And you can go back and look at the video if you want for the other one. Okay? Yeah.
Everybody get this?
Just wondering, for these types of questions, will they ever like not be able to be proven?
Okay, so that question was asked earlier. Yeah, just two random statements might not be able to, aren't identities, but what we're, I believe for 99% of all the questions you're going to get here, they're going to be like, this is an identity, prove it. So that's the idea, to prove it. So yeah, you should be able to get down to both sides being equal. All right, here's some tips. So jot these down. I'll give you time to jot these here down. So one of the main tips is to express your trig functions in terms of sin x or cos x. Express your trig functions in terms of sin x or cos x. That's one tip, and you've seen me do that on this last one. Okay, so tip number one. It's a good one. Tip number two. Focus on only one side of the equation. Okay, that's my tip number two. Focus on one side of the equation, because if you start changing both, you might kind of miss something. Okay, take a step and you might start to go, they might start to diverge instead of, so it's always good to keep kind of one side in mind. The third one was is to focus on the more complicated side first. Okay, so pick the more complicated side because you have just more material to work with there. There's more options for substitution. So the complicated side. Okay, so if you run through those ones and you're like, oh, I don't know what else to do. Number 4 for tips would be perform the indicated operations. So perform the operations. If you have two terms on one side, then go ahead and add them together or subtract them or whatever. If you have multiplication, you can multiply them in. Maybe something will cancel out, but perform the indicated operations. You'll see that a lot, that you'll have to do that. The last two, and again, there may be others as we move on, but now it starts to get to more complicated ones where it's like, okay, I've done all this, I still can't see that the left side might equal the right side. So number 5 would be factor. Factor the expressions, either difference of squares, trinomials, like quadratic. So factoring and splitting things up, you might be able to divide something out. So factor and remove common factors. That's a good one. And finally, I might get to an example today of this one. Number 6 would be to multiply the denominator by the conjugate of the expression to get a difference of squares.
That's the opposite one, right?
Yeah, that's like the same, says the same binomial terms, but with the opposite sign in the middle. Yeah, and I'll show you an example of that. So, yeah, just go ahead and jot it down for now, and then it'll make sense once we do some examples. You'll be able to look back. Okay, so if we're to prove this example right here, 1 minus sine all squared plus cos squared equals 2 times 1 minus sine theta. Yes?
The right side is it's supposed to be a square.
Oh, did I erase something accidentally? Which example is this one? Okay, it's not written incorrectly. We're trying to prove this. Okay, so prove that this is an identity. Let's see if we can do that. Okay, so the more complicated side would be this side on the left. Okay. So everything is in terms of sine and cos. We look back to our tips, right? We're going to manipulate one side, the more complicated side. That's the left side here. So I'm going to perform some indicated operations to try and either gather some like terms, reduce some things. So I see that I have 1 minus sine theta all squared. So I'm going to do this. I'm going to actually square this out. So that's going to be 1. It's going to be a FOIL, right? And for those of you that aren't seeing this, it's going to be like this, right? FOIL. So 1 minus sine, so it's going to be minus 2 sine theta.
Oh, this is crazy.
Not really. And then plus, so 1, and then minus sine theta minus sine theta. There's 2 sine thetas that we're subtracting, so that's minus 2 sine theta. And then the final is a negative sine theta times a negative sine theta, which would be plus sine squared theta, right? And then we've got plus cos squared theta from before. So I'm just foiling out this this part right here. So this right here is this right here when it's multiplied out, right? Does that look good? Yes? Question?
Why wouldn't we have just changed the 1 minus sine theta to cos x, or to cos theta?
Okay, why wouldn't we just have changed the 1 minus sine theta to cos theta? Because it's 1 minus sine squared theta. It's not 1 minus sine theta.
Will that not just change it to?
No, 1 minus, okay, so 1 minus sine squared is cos squared, right? This is this. But 1 minus sine theta is not equal to cos theta, which is what I heard you say. Is that what you're suggesting?
Oh, it's a little arm.
No, can't do that. This one's good. This one's good here. This one's not good. No good.
So would 1 minus cos x squared equals sine x squared? That's like also a thing?
What?
1 minus cos x squared would equal sine x squared.
Yes. Yeah, squared x, yeah. All right, so what pops out of you here, guys? Anything jump out at you on this side that I can substitute? Any identity that you see there? Luke?
Could you make sine squared plus cos squared be 1?
I sure could.
Oh my goodness.
Oh, yeah, that's
Right there.
Oh my goodness.
And then you have negative 2.
No
Ah,
way.
you smart fella.
Oh, what the heck?
So this is 1. So that's 1 from identity, right? See that?
Oh,
Now you see that we have 2
you cancel them out.
minus 2 sine theta.
Oh, yeah, sorry.
And then factor 1 minus sine theta.
Oh my. My goodness.
I love the shocked expressions when this actually works out. Because that's an identity. 6.1. That's our first. That was our Pythagorean identity. Sine squared plus cos squared equals 1.
Getting something.
Okay, we're not done yet. So I've kind of highlighted here that the left side equals the right side. So Sir Isaac Newton would be really happy if you put QED there at the end. Okay? Next one. Prove 1 minus cos x over sine x is equal to sine x over 1 plus cos x. Prove that that is an identity for all possible values of x. So we are again going to manipulate one side, make it look like the other. And I'm going to focus on both sides because they both look equally kind of complicated, right? So we'll do one side, make it look like the other, and then we'll do the other side.
Ready?
Oh.
Okay, ready? I'm gonna do this.
Okay, you guys want to give this one a try on your own?
Yeah.
Okay.
Okay.
Okay, I'll give you a minute. Do this one on your own, see how far you can get. Okay, so with this one, do you see an identity in there that you can replace? Like, is there an obvious identity?
Let's check.
I mean, you could divide
Okay.
out.
Okay. Okay, so cos over sine, you could manipulate this so you have a cotan. You could, but even cotan is like, there's cotan squared is going to be a thing. So that would be a little extra work, but you could do that. Let me show you guys. So this is a tough one. This is a little bit of a tougher one. But if you had to start, that's great. So look at the tips and tricks here. Remember the tips? This number 7 here that we talked about, the conjugate, that's what we're going to want to imply here, to apply. Guys, just let me explain. So the reason is because 1 minus cos squared x is an identity. You can change that. Sine squared x is an identity. You can change that. But we can't just do without squared. So we want to try and get a squared something. So I'm going to focus on the right side first. And I'm going to multiply by the conjugate of 1 plus cos x. That's 1 minus cos x. And what I do to the bottom, I have to do to the top. Because it's like I'm multiplying by 1, you see? So this is the conjugate of this denominator here. Where it's 1 plus cos x, the conjugate is 1 minus cos x. Same terms of the binomial, opposite sign. So now what we're going to get, when we do that, it looks like, oh, why would you do that? But watch this. On the bottom, look at what I get on the bottom now. I get 1 minus cos squared x, because it's a difference of squares now. Because this is the factored form of a difference of squares, you see? So when you multiply it out in the bottom, you get 1 minus cos squared x. Now, the top, now watch this, guys. Be careful with the top. If you go ahead and multiply this in, you're going to have sine x minus sine x cos x. Now, sine x minus sine x cos x, there's nothing in there that is an identity. Okay? Sine x cos x, that's not an identity. That's not in your list of identities. So sometimes you don't want to multiply things through, only if it comes to something that's useful. And this is what's going to take some practice. So you don't have to multiply everything. I would leave this like this, sine x, 1 minus cos x. Okay? You can do that. Because again, factoring and manipulating, dividing out is a key thing. So I'm going to leave these as factors. Okay? So now what do we have?
Sine x squared up.
Yep. This right here is an identity, guys. So I'm going to write sine x times 1 minus cos x all over sine squared x. You see this?
And then you can do the thingy. Yeah, wait.
And now we're very, very close to being done. Because if you divide the sine x, and look at this, one of these sines, one of the squareds there.
Oh, so you get 1 times 1 minus cos x. Over sine x. Or sine, yeah, sine x. Spicy. What? Oh, it's the same. Oh my god.
But they don't cancel out. One is just a sine x on top, the other is a sine squared x on the bottom. So I canceled the two already. So, everybody see that? So that works. And if you chose the left side because you didn't really know which one was more complicated, because some of you have asked me that, I'm like, which one's more complicated? Well, they're both about the same. So watch what I'm going to do here now. I'm going to do the same sort of thing to the left side, and you'll see that we're going to get this now. Okay, so watch. I'll do this a bit quicker because I've already done it once, but if you multiply by the conjugate, top and bottom, it really is the exact same thing. We get 1 minus cos squared x on top. I'll leave this in factored form. The 1 minus cos squared x is actually going to go to sine squared x, right? And then you do the same thing. This sine cancels off with one of those signs, and you're left with sine x over 1 plus cos x. And this then will be the same as this one. You see? That's the same as that. This one's the same as this. So it doesn't matter which side you choose. In this case, you can manipulate both sides. And if you, I guess, the other thing is if you went halfway to this stage, and then halfway to wait, oh, wait, what? Oh, to, maybe not, sine x over sine squared x. No, you can't go halfway, sorry. I guess it won't work. Forget that. Okay, if you take this one step at a time, it's not impossible, okay? You can do it. You can do it. All right. No 6.4. We're not going to do 6.4. All right. Okay, guys, write this one down, please. This is part of your assignments, I believe. one of the questions nearby? Well, this isn't your assignment yet, but this is 6.3. This is from 6.3, 2D. Okay.
Oh my goodness.
It says 6.3, 2D. Yeah.
Hold on.
Oh,
I think.
All right, so this one, okay, already we're 4 or 5 in here. This is getting complicated, but this is another type of question that I want to highlight for you. All right, yeah?
Is that a quadratic on the bottom?
Yes, it is a quadratic on the bottom. Thank you very much. So this is a constant, 2 sine x, and then sine squared x, right? So yes, this is a quadratic on the bottom. And what we're going to want to do is we're going to want to factor this quadratic if we can. And it might be a good idea to factor this too. This is a difference of squares. So a difference of squares and a quad. Okay? So here we go. This is going to be 1 minus sine x times 1 plus sine x on top. Now this one, okay, you might not like the look of this, but this is the same as, boys, geez. This is the same as 1 minus 2x minus 3x squared. You see? So here's your variable, and here's your variable squared, see? That's why it's quadratic. So it's the same form as this one. So how would we factor this one? By sight? It's going to be a little tough, right? 1, 1. It's going to multiply to 1. And we need 3x squared. So we're going to do 3x and x. And then we got to figure out our signs. So if we go minus 3x plus x, we get 2x. So this is big kid math here. You guys got to have a handle on factoring quadratics too. So what I want to show you is that this actually can be factored to 1 minus 3 sine x times 1 plus sine x. Because we let x equal sine x. Yep. What's 1 plus 2x? What did I miss? Oh, it's 1 plus here. Oh, shoot. You're right. It is. Okay, that's fine. So then we have plus 3x and minus x. Yeah, thanks for noticing that. So this is plus, and this one's minus. That's exactly right. Okay, again, this is one of the tougher ones already. Okay, in the lesson here, this is one of the tougher ones we're going to see in the lesson. So you're going to get lots of practice with the easier ones too. Don't worry. So now, can I cancel anything or divide anything out? I can do this and this. And is that pretty promising? Yeah, it is. 1 plus sine x over 1 minus 3, and we're done.
Wait, is it minus?
Wait, it's supposed to be plus.
Plus. Sorry, I didn't change that one. So there we go. That is our QED. We're done.
they already have
Wait, can you keep our reference there?
Yes, I'll keep this up.
What does QAD stand for again?
It's QED, quod erat demonstrandum.
Dang. Word.
Words. Okay, so I'll give you a 6.3 assignment here.
Do you have a fifth period? Nope.